Okay, so welcome to the, I think, first online seminar of the series, and it's already nice to see all these nice people around. And so our first speaker is for this event is Aleix Gimenez-Grau from IHES, and he's going to talk about his recent paper with Slava and Yuna Nakayama on scale without conformal invariance in dipolar ferromagnets. Please, Aleix, thanks a lot for being with us today.
Yeah, no, the opposite. Thanks for the invitation. I'm really happy to be here. And as you were saying, yeah, I'm going to talk about this paper that we wrote recently with Slava and you. And let me give a very...
les écouteurs, il n'y a pas de doute. Je suis un peu désolée.
I guess someone has to mute themselves.
Yes.
Okay.
I will mute myself, but yeah.
Yeah, no problem. So let me briefly summarize the outline. So I will start with some motivation, and then the talk is going to be divided in two main points. Like the first section, this section number 2, is going to be about the dipolar model and some experiments. So this part is, let's say, a bit more physical. And then there's going to be another section which discusses the issue of scale without conformal invariance. So this one is maybe a bit more formal. And I'm happy to skip maybe one section, or like, I don't know, skip parts of some other section. So let's see how it goes. But let me know how I'm doing with time. Okay. So let me start with the motivation. So the type of system we are going to study today is what we have to have in mind is something like an isotropic ferromagnet. So as we all know, like you can tune the temperature of a magnet, and then below some critical temperature, this magnet is going to be in some ordered state. Okay, and then if you heat it up, if you go to a temperature which is high enough, then this magnet is going to be disordered. Okay, and then precisely at the critical temperature, which sometimes people call the Curie temperature, interesting things are going on, and in particular, there's some correlation length which becomes very, very large. Particularly, it's much larger than the lattice that you are studying. Okay, and then in this limit, what you have is that you have some kind of continuum field theory. Okay, so in particular, we are going to be quite interested in being like near this regime of this critical temperature. Now, a piece of lore that many people repeat again and again is that if you have a ferromagnet, then when you are near the critical point, the physics are described by, on one hand, the Heisenberg model. Like this Heisenberg model, it also has some critical point, and presumably it should describe some ferromagnet. And then in particular, this critical point, what people say is that it's actually a conformal field theory. Like the continuum field theory that describes it enjoys conformal invariance. Okay, so the goal of this talk is to actually argue that these 2 points are not really correct. And the correct thing to say is that actually a ferromagnet at the critical point is described by something that I'm going to call the dipolar model. I'm going to introduce what this is later. And the second point, which is very important, is that this dipolar model is not actually a conformal field theory. Instead, it's a scale invariant field theory, which doesn't have conformal invariance. Okay, so that's the main point of the talk, to argue that these 2 pieces of lore that everyone believes, even though they are good approximations in some regimes, they are not entirely true. The true story is really like this dipolar model being scale invariant and not conformal. Okay, so that's the main message of the talk. And here, this should raise, let's say, some questions. The first type of questions, they are more like experimental. No? So if experiments agree with Heisenberg model and like everyone repeats this lore that I was saying before, how come that people don't talk about dipolar effects, right? Like what type of experiment should you do to see these dipolar effects, etc. And that's what I'm going to try to discuss in the first part. In the second part, I'm going to discuss something which is a bit more formal. And this thing is the story of when a conformal, when a fixed point like of the RG flow, when do we expect it to become a CFT, and when do we expect it to only be scale invariant. Okay, and in particular, I'm going to show that there's something special about this dipolar model that makes it be scale invariant and not conformal. And I'm going to show that this thing which is special, it's actually shared by many other models that we've studied. So that would be like the summary of the talk. And as I was saying, like it's going to be divided very much into two different parts. Okay, so is there like any question at this point, or if not, I'm going to proceed with the first part. And please interrupt any point, like if there's any questions. So let's start with the more experimental part of the talk. And in particular, I'm going to start with a very, very brief review of magnetism. Okay, so the picture to have in mind is that you have a magnet, and a magnet is just like a bunch of magnetic dipoles. Okay, so when I was drawing this picture, what I have in mind is that each of these arrows is a magnetic dipole. And these dipoles, they experience two different types of interactions. So on one hand, they have what people call exchange interactions, and on the other hand, they have dipolar interactions. Like typically people only consider these interactions, but I'm going to argue that these ones are actually very important. Okay, so let me explain what are these two things. First, starting with these exchange interactions. So let's imagine like a very simplified model where you have two spins in your magnet. So now if you take these two spins and they are very far away, you can just imagine that there's like 4 energy levels, right? Like you can have something like spin up, spin up, spin up, spin down, and so on and so forth. And because these two spins are decoupled, all these states, they have the same energy. Now, if instead you turn on some type of interaction that preserves the rotational symmetry of the system, what's going to happen is that these 4 energy levels, they are going to be like split between some irreducible representations of the total spin. And in particular, there's going to be 3 states which have a certain energy, which are like a triplet of SO3, and then like a singlet state which has a different energy, right? And this can happen in 2 different ways. Like the triplet might have higher energy, or the singlet might have higher energy. Okay, and that's what physically is the difference between a ferromagnet and antiferromagnet. Okay, and the point is that once you have like this type of situation where some interactions separate the energy levels between a singlet and a triplet, you can actually model it with some Hamiltonian of this form. Okay, so that's the usual Hamiltonian that people use in the Heisenberg model. However, the whole point of this talk is to argue that this is not the only type of interactions experienced in a magnet. So in particular, there's also dipolar interactions. Okay, so for people studying physics, this is very clear. So each of the spins in a magnet is actually a very tiny dipole, like maybe infinitesimally small. And a dipole, by definition, what it does is that it creates some magnetic field. Okay, so this is what this figure is depicting. And in particular, you can write some formula for it. So if you have some dipole, like this is the strength of the dipole, then you can measure like the magnetic field at some position R, and it's gonna be given by some formula. Like this is a standard formula from undergrad physics. And that's one part of the story. And the other part of the story is that if you have a dipole and you put it in some magnetic field, then it also experiences some energy. So there's some energy which is like negative S times B. So in particular, when you combine these two equations, it turns out that whenever you have a pair of dipoles, each dipole generates a magnetic field, but then the other dipole, it's in this magnetic field, so then it experiences some energy, like the system itself has a certain energy. And that's what that's the type of contribution we wanna take into account in this talk. So in particular, if you have, for instance, 2 dipoles at positions 1 and 2, this would be the energy felt by the system of 2 dipoles. Okay, so it's like it decays with the distance, but it decays like a power law. So it's like some kind of long range force. Okay, so this is what we are gonna add to our Hamiltonian. And to keep the notation simple, what I'm gonna do is that as you see, like this energy is proportional to the 2 dipoles. So I'm going to factor out the contribution of the two dipoles, and then I'm going to write some function that I'm calling U, which is some kind of dipolar potential, let's say. Okay, so that's some kind of replacement for the Coulomb force. In this case, since we study magnetism, the Coulomb force doesn't apply, but instead we really look at this function Uij. Okay, so that's like the summary of the two contributions. And as I was saying, what we want to do is we want to build a Hamiltonian that contains both of them. Okay, so these exchange interactions, they are typically like very short range. So then what people do is that they model it with some sum over nearest neighbors. Okay, so you compute some energy, which is a sum over nearest neighbors, and then you just multiply the spins in this nearest neighbor site. And then we have some dipolar term where we have to sum over all positions. Because this term is long range, you actually have to consider all the spins in your model. And for each of them, the potential is proportional to this function U that I just defined, and you just include the factor 1/2 because you avoid overcounting. Like each pair of spins contributes only once to the energy. So now that we have like this would be like the lattice system, what we want to do is that we want to take some kind of continuum limit. Okay, so we want to tune the temperature. The temperature is like here, like yeah, you can rescale like this J in such a way that like the temperature would enter. And then you can tune like near like your parameters near the critical point. So near this critical point, what's going to happen, as I said before, is that the correlation length is going to be much larger than the lattice spacing. So what we can do in this regime is that we can do what I'm going to call coarse grain averaging. Okay, so what coarse grain averaging means is that so you have like some lattice spacing, which is very small. Then you have some correlation length, which is much larger. But then you have like the size of your sample. So what we want to do is we want to average in some intermediate scale. So we want to average over many, many lattice sites. But this region over which we average, it still has to be much smaller than the whole sample. Okay, so if you do this type of average, then this field phi is going to be some continuous field. And then we can write some continuum field theory for it. Okay, so this procedure of coarse grain averaging is actually standard. And it's well known that if you start with this Hamiltonian here, which is the Heisenberg model, what you end up with is some kind of phi to the 4th theory. Okay, so there's some kinetic term for this field phi. Then there's some mass, and the physical meaning of the mass is that it roughly measures like how far away you are from the critical temperature. And then there's some coupling lambda, right? And then this has to do with the fact that like this, at the critical point, this theory behaves like in a very non-trivial way. Like there's non-trivial like interactions between different types of fluctuations. And that's captured by this phi to the 4th term. And then besides this, since here we are considering like this extra dipolar term, we are going to get an extra term in our Hamiltonian. So this extra term is going to be non-local. Non-local in the sense that we integrate over two different points like x and y. And then what we integrate over is essentially like this dipole-dipole potential that I introduced before. Okay, so that's the model that we want to study. And now the question that one can ask is, okay, so which one of these two parts is more important, right? Like, is this blue piece more important, so then Heisenberg behavior dominates, or is this green piece more important and therefore like dipolar effects dominate? And the notion that allows you to distinguish between these regimes is something called the crossover. Okay, that I'm going to explain now what this means. So the idea is the following. Once you study like these statistical systems using RG, what you are interested is in seeing like how the different couplings in your energy functional, how they evolve as you change the scales at which you look at the system. In particular, by dimensional analysis, you see that this coupling V here, it actually grows. Like it's strongly relevant. It's in fact as relevant as the mass term. So in fact, it's gonna go like it's gonna increase like a power law in the infrared. So what's gonna happen is that as you keep going in this RG flow, this V is gonna get larger, larger, and eventually this term is gonna dominate over this other term. Okay, so that's what I mean here when I say that this coupling V is strongly relevant. Okay, but then like the way to understand this type of behavior, it's very nice to look at it in some kind of picture. So let's imagine that you have some material, right? Like a material has like certain spins inside, and then depending on the type of material, you're gonna land on some effective Hamiltonian that has different parameters. Okay, so like these different couplings here, like M, lambda, V, they are gonna be different for different materials. Let's say iron, nickel, europium oxide, whatever. So now for some materials, like in the UV, like this V is gonna be like some large number, like some order 1 number, let's say. And then when you do RG flow, what's gonna happen is like you have some trajectory that lands directly into some dipolar fixed point, let's say. So actually, maybe let me explain a bit better like this figure here. So here what I'm trying to represent is like the different couplings in our theory, right? So we have one coupling which is lambda. We have like the mass squared, and this mass squared, like we tune it to 0 to have like a critical point. And then we have like this V, which measures dipolar interactions. So there's gonna be like 4 different fixed points. This is the Gaussian one, where all the couplings are tuned to 0. This is the Gaussian dipolar, where like this lambda coupling is tuned to 0, but there's dipolar interactions. This is the Heisenberg fixed point, where the dipolar effects are tuned to 0. And then this is the dipolar fixed point, which is the new fixed point that we are studying in our paper. So the idea is that we are interested in understanding like how do the RG trajectories look in this phase diagram. And then what's gonna happen is that depending on the material, like the initial point of your RG flow is gonna be different. So for some materials like this trajectory number 1, like the V you start with is already kind of large, and then you flow directly to some dipolar fixed point. What this means is that when you do an experiment, you are going to see dipolar effects right away. Instead, there's also some materials that have like very small intrinsic dipolar effects. Okay, and then the reason, the fact that they are very small means that when you start in the UV, before doing your RG flow, your coupling V is very small. And then in this diagram, what this means is that you start your RG flow like very close to here. You start like very close to V equals 0. So you start close to here. And then when you follow your RG trajectory, for a while, you are going to be very close to Heisenberg. But then at some point, eventually, like you are going to land on dipolar. So when you do an experiment, I'm going to explain later what it means to follow this trajectory when you do an experiment. But the thing to keep in mind is that you would do an experiment and maybe you would see Heisenberg behavior in certain regimes, and you would see dipolar behavior in some others. And that's the reason that people usually ignore dipolar effects, because they do experiments with low resolution, and then they say, oh, well, like we are just seeing Heisenberg behavior. But in fact, the claim is that if they actually increase the experimental resolution, they will eventually end up like observing dipolar effects. Okay, so are there questions at this point? Like this is an important point. I hope it's more or less clear what I'm saying.
Very clear, very clear.
Yeah. Okay, perfect. Thanks. So what I'm going to explain now is how do you make this discussion a bit more quantitative? Okay, so as I said, like I said something a bit vague, like, well, sometimes you do an experiment, sometimes you are in the Heisenberg regime, sometimes you are in the dipolar regime. Now what I'm gonna do is make this a bit more quantitative. Like how can we tell, like, if I give you a material, like, are we following this trajectory number 1? Are we following this trajectory number 2? Like, if we do a particular experiment, like how far along this this RG flow are we doing the experiment? That's what I'm going to try to explain now. And to do it, I'm going to focus on mean field theory. Okay, that's just to simplify the discussion, but everything carries over to the interacting theory. Okay, so mean field theory basically means that I just turn off interactions. And it's convenient to just take a Fourier transform. So instead of, if you remember, that was our Hamiltonian, I get rid of this term here. So I turn off interactions. And then this thing is quadratic in the fields. So it's phi squared, and phi squared. So then you can just Fourier transform. That's what I'm showing here. You can just Fourier transform. And what you obtain is that there's some kernel in your Fourier transform. And that in physics is what we know as the inverse propagator. Okay, so this object here is going to be the inverse propagator. And now by looking at this propagator, we can just invert this equation and we can compute what this G is. And we are going to observe two different regimes. So in the first regime, imagine that Q squared plus M squared is much larger than V. Okay, so this means that this Q squared plus M squared is much larger than V. So then this term dominates. We can neglect this term. And what we obtain is that the propagator is the usual propagator we are used to in the Heisenberg model. Okay, and then instead, in the opposite regime, when V is large, this term dominates. And then you can do a calculation, which is not hard. You can invert this propagator, and you find that G takes the following form. Okay, so here, when I have like these two columns, this is what I mean when I say that like you are doing an RG flow and you are like at a certain point in the RG flow. So when you do the RG flow, what you are doing is that you're actually lowering your mass, so you are getting closer to the critical point, and you are doing experiments with a smaller and smaller Q. Okay, so you are looking at some Qs which are smaller, which means that you are doing experiment at longer and longer distances. Okay, so then doing an RG flow means changing the relative size of this term compared to this term. Okay, so the claim is that if, for instance, you look at the propagator and your parameters are such that like Q squared plus M squared is large, then you are going to be in this regime. If instead you tune your experiment such that that Q squared plus M squared is smaller than V, then you're going to be near this point. Okay, so that's like quantitatively, what does it mean like to have like these different types of trajectories? Okay. And then in particular, what we want to do is that we want to have like this criteria, which tells us like how far are we like in this RG flow. We want to convert it into something that it's easy to compare for different materials. So that's here. This is a slide. So again, like to insist a bit once more, we want to compare Q squared plus M squared with this parameter V. If we want to have dipolar effects, M has to be much smaller than the square root of V, but also Q has to be much smaller than the square root of V. Okay, so that's the conditions that you need to observe dipolar effects. And what we want to do is we want to convert this into something that we can compute for different experiments. So in particular, we came up with a way, like it's not terribly important, the details, but we came up with a way to transform like these conditions, this condition here into a condition on the reduced temperature. Okay, so in particular, having a mass which is small means that being the equivalent to tuning your temperature very close to the critical point. So in particular, you can translate this into some reduced temperature criteria. So this means that having some reduced temperature T, which is much smaller than some TD, like T dipolar, which depends on each material. Okay. Is this idea clear? So for instance, here, I'm showing different materials, and then I'm showing what TD is and what QD is. For instance, for like these materials, they have like really strong dipolar effects, this T and this Q, they are quite large. So it means that whenever you make the temperature very close to the critical one, you are already going to observe dipolar effects. However, you have other materials like iron and nickel, where this TD and QD, they are actually quite small numbers. And what this means is that you can actually make TD quite small, but still larger than TD. And then,
sorry, what is a
yeah.
TD? How is it defined? TD?
TD is just like some rescaling of this equation. So you have to imagine that M is essentially like the difference in between T and TC. So what I'm doing here is just like rephrasing this equation in terms of some reduced temperature.
Okay, thank you.
And now if here I'm skipping some details, but like one of the nice things in our paper is that we kept track of a bunch of numerical factors, and then we give some formulas for TD and QD, and
Okay.
we give some way to estimate these numbers.
Mm-hmm.
So then, but thanks for the question, and please ask more if like either you or other people have questions. So indeed, the point is that like we have a way to estimate these numbers, and then when you have these numbers, then you can see, okay, let's say you do an experiment at a certain reduced temperature. Now you go to this table and you say, okay, is my reduced temperature much smaller than TD? And if it is, then maybe I'm observing dipolar effects. But if actually like I don't have like enough experimental resolution to have like reduced temperature much smaller than TD, then I'm only going to observe like Heisenberg behavior. So that's the main message of this slide. Okay, and that's like important because then it allows you to tell like for people trying to observe this behavior if they're actually close or far away from achieving it. Okay, sorry, let me see how I'm doing with time. Okay, perfect.
Yeah, you are. I think you have like
okay
an hour.
half an hour. So then maybe I can skip the next slide. It's not very important. It's just like the whole message is that there were some people like in the 80s that they did some experiments and they actually managed to observe some dipolar effects in certain materials, but it's some story that it got a bit forgotten. And it would be nice, like nowadays, apparently like these techniques that they used, they have improved a lot. So it would be nice if like experimentalists try again to observe these things, because like right now, like we might be able to see this in much better resolution. But let me not go into the details since part of the audience are not physicists. And instead, I'm going to jump to part 2. So it's a good moment to ask questions if you have some.
Yeah,
And
so
if not,
I have a question.
yeah,
very quickly. So then.
No, please.
So you're saying that these dipolar effects are actually much more common than the Heisenberg effects, or not? Like
yes, correct. So the comment is that if you actually wanted to, so let me go back to this Hamiltonian. The comment is that here this coupling V, it might actually be quite small in many materials, but still it's a relevant coupling. So in the IR, if you go like far enough in this RG flow, if you go like close enough to the true IR fixed point, actually this is gonna eventually dominate. And it's like the new fixed point that you study is really like this dipolar fixed point that I'm talking about. So the point is that like the reason that sometimes people only see Heisenberg behavior is because they are actually doing experiments at very little resolution. Like if they actually manage to get like really, really close to a critical temperature and measure things at very long distances, then they actually should see dipolar effects. And this is something that very few people have explored. So that's one of the main messages of our paper, that it would be nice that people like go back and review whether these things work out or not in practice.
But if you are at the Heisenberg fixed point, Like
then this v would be exactly 0 in the Heisenberg fixed point.
yes,
But the point is that no
but
matter how
I understand.
Okay,
Like
sorry, go.
imagine you are at the Heisenberg fixed point, then
Yeah.
does the Heisenberg fixed point have like a relevant operator that can be added in order to deform it away?
Yeah, that would be this term. This is a relevant term. So like here the question to maybe to rephrase a little bit is so abstractly you can just imagine that you set this coupling to 0. Like that's perfectly fine, like in our like theoretical world. But the comment is that in practice, in materials, you cannot really like set this thing to 0. Like in a Monte Carlo simulation, you can set it to 0. That's fine. But in a real material, there's always dipolar interactions. Like they might be small, but they are always there. You cannot really tune this thing to 0. Like there's no mechanism we have to tune it to 0. So in real materials, this is always going to be there. It might be small, true, but it's always going to be there. And as you keep doing more and more precise experiments, eventually you are going to see it. So that's the message.
For each material, I guess people measure this V value.
Yes,
somehow.
precise. Yeah, so the point is that you can do experiments far away from the critical point, and then you can fit certain curves. You can see how certain quantities behave, and that allows you to estimate this parameter V, this parameter M, this parameter lambda. And once you have these estimates, it allows you to tell you, okay, how close should I get to the critical point to see dipolar effects? So that's the message. Any other questions? If not, I'm going to move on to a slightly different topic. So maybe a bit more formal. Perfect. Then I'll just move on. So let me give a different perspective on this whole discussion that I just had, and now I'm going to forget about experiments. Okay, so let me work in momentum space, and the term that we were adding to our usual Heisenberg Hamiltonian in momentum space, it looks like this. Okay, and then I was just saying that this coupling V, it actually grows in the IR, so it means that we can take V going to infinity. So when this V goes to infinity, we can think of this as some constraint that forces the fact that Qi times phi I has to be 0 at the fixed point. Okay, so because V goes to infinity, in the IR fixed point, Qi times phi I is going to be 0. Okay, or in other words, in position space, this translates into the fact that phi I has to be conserved. Okay, so that's like heuristically what this dipolar term is doing. Like it's suppressing like longitudinal fluctuations, but the transverse fluctuations stay the same. Okay, so that's one way to think of the effect of dipolar effects. Let me give a different perspective on what's going on. And let me instead of using, so this action here is non-local, but actually I can describe the same physics using an action that is perfectly local. Okay, so
sorry, Aleix, I'm a bit confused
yes.
by the indices. Like
Yes.
what is delta I and phi I as well? Like I think the I index labels.
That's a very important point. I should have explained this. So we have two concepts, which one is space-time. One is space-time, and then it's like, let's say we are in 3 dimensions, so then we have like 1, 2, 3. Another one is like global symmetry, like global symmetry. And then like we also have like, sorry, like for space-time, let's say like people would usually call like this mu. And then for the global symmetry, people would typically call this I. And since we are in the O3 model, this runs over 3 numbers, like 1, 2, and 3. But here the point is that dipolar effects, they are coupling the position, like they are coupling like the direction of some spin. It's actually coupled with the like let me show you some equation before. So here when you see like such an equation, you are multiplying here some global symmetry indices with themselves. So that's fine, that respects O3 symmetry. However, here you are multiplying some global symmetry indices with some space-time indices. So in fact, what you are doing is that you are breaking this, you're breaking like some O3, which has to do with global, times some other O3 that has to do with the space-time, space. And you are breaking this to just some diagonal subgroup. And that's the reason why everywhere I'm using like these IHES indices. Because they are both global and space indices. Like it's, we are allowed to mix them up. Is it clear?
Yes, thank you.
Yeah, and good question. I should have mentioned it before. So indeed here, this equation, it's a bit confusing because sometimes people might, I don't know, it would be something like d mu phi I, right? Like that's the type of indices we are used to. And here instead we are contracting them with each other. Yeah. Okay, so just to come back to the discussion we were having, I was saying that the effect of dipolar interactions is essentially to suppress longitudinal fluctuations. Okay, to the fact that phi becomes like a conserved field. And we are going to model this with some local Hamiltonian. So how do we do this? Like the idea is that actually like this dipolar system that I'm talking about, we could think of it in terms of this Hamiltonian here. So in this Hamiltonian, I just have like the field phi and its mass and its quartic interaction. And then I introduce some magnetic field P. Okay, so this magnetic field, it has some kinetic term. That's like the kinetic term for B. And then the magnetic field is coupled to phi. So what am I really doing here? Like I have like some spins. And then I'm saying that these spins interact through dipolar effects. What I'm saying is instead of saying that they have like some non-local interaction, I actually introduce some other thing that I call B, which is the magnetic field, that is like the field responsible for this interaction. Okay, so I'm integrating in the magnetic field. This field is dynamical. Now, if I integrate out B, like here I can like B appears quadratically. If I integrate it out, I recover the original dipolar Hamiltonian. Okay? But in fact, once I have like this action here, I can do some massaging that I'm not going to show you. And I can show that, that this Hamiltonian is also equivalent to some other Hamiltonian where you just have phi with its mass and its cubic interaction, its quartic interaction. But then you have an extra field U, which acts as a Lagrange multiplier, and it enforces this constraint. Okay, so here what I'm showing is that there's, between the Hamiltonian I was talking about, we can transform it to some other Hamiltonian which depends on some new field B. And then after massaging a little bit, I obtain that this is equivalent to just having our original Heisenberg model with the local constraint that di phi I is equal to 0. Okay, so that's the thing that we want to study. That describes the fixed point in a dipolar model. Okay, is this point clear? Okay, hopefully yes. And if not, please
Very
stop.
clear, don't worry.
So now, as I was saying, phi in this dipolar fixed point is going to be a conserved field. And what does this mean? Well, we can write down like the 2-point function of phi. And what form does it need to have? Well, it has to have like some 1 over x to some power that's fixed by scale invariance. And then the fact that there's some rotational invariance, it forces us to have only like some object, like some Kronecker delta, or then this tensor structure here, xi xj over x squared. Okay, so that's the most general answers we could have for this 2-point function. However, I was just saying that in the fixed point, like the fixed point we are studying, phi has to be conserved. Like the divergence of phi has to be 0. So in fact, if you take these ansatz and you impose this constraint, it turns out that alpha has to be fixed. Alpha in particular, take this value here. Okay? And now here you are almost done. So because remember that in CFT, like if this theory, like this fixed point that we are studying, if it was a conformal field theory, then you would see that alpha has to be equal to 2. Like this is something that people like do in like introductory texts on conformal field theory, and they see that conformal invariance fixes this number to be 2 if phi is a primary operator. Okay? But now here I'm saying that, well, no, actually alpha has to be this number here. So we just have to compare like this number with 2. And then if there's no match, then this theory cannot be conformal. Okay, so let's do some explicit calculation in 4 minus epsilon dimensions. And what we actually see is that phi has some like the usual formula, no? It has 1 minus epsilon halves, and then some epsilon square correction and some epsilon 3 correction. Like this is like something that requires a lot of work to compute. But even already like the 3-level result is very easy to see. And already at 3 level, you would see that there's a mismatch here. And like if you plug in this number in this equation, you would see that alpha, like I don't know, it starts at -2 plus epsilon plus blah blah. So then at least in the epsilon expansion, it's definitely clear that like this alpha here and like the number that is required for a CFT, they are different. Okay, so we conclude that this fixed point is a scale but not conformal invariant. Okay, so just to summarize, 2-point functions in this model, they are in contradiction with conformal invariance, and therefore like this theory can only be scale invariant. Okay, that's the argument. It's actually very simple. But now this actually raises some puzzle. So perfect. And the puzzle, it comes from some paper in the 80s by Polchinski. So what Polchinski observed is that if you have a theory that is a scale invariant but not conformal invariant, what you need to have is that the trace of the stress tensor, it's actually the divergent of some operator V. And this operator V, it cannot be conserved, okay? Because if V was conserved, then this trace would be 0. And if the trace is 0, you recover conformal invariance. Okay, so what this is saying is that in a theory which is a scale but not conformal invariant, there has to exist an operator V that people call a virial current, and V is not conserved, but in fact it has dimension d minus 1. Okay, because you can just like the stress tensor always has dimension d, like the derivative has dimension 1, and therefore V needs to have dimension d minus 1. And the puzzle goes as follows. Okay, so you have some operator which is not conserved. You have some theory that is interacting. How can it be possible that this operator is actually not renormalized? Okay, so that's the puzzle. So what people say is that, okay, in a generic theory, there's going to be interactions. So any operator that you think, maybe this is the virial current. Well, this virial current is going to receive some quantum corrections, and then it's never going to have dimension d minus 1. So in general, what we expect is that any interacting theory in a fixed point, it's actually going to be a CFT. And the reason we expect this is because it looks like there cannot be a virial current. Okay? So that raises the puzzle. How is it possible that our theory, which looks like perfectly normal theory, how is it bypassing this argument here? right? Like this might look a bit confusing. And let me go into it in a bit more detail. So recall, the Hamiltonian is just like some kinetic term for phi. We have some mass term, which we tune to 0 to be near the critical point. And we have some interactions, lambda phi 4. And then we have an extra term here, which is like some Lagrange multiplier enforcing that phi is conserved. Now, if you take this Hamiltonian, it's not hard to compute the stress tensor, and then you can compute its trace. And then what you see is that there's some, like the trace of the stress tensor contains some virial current, which is U times phi I. And now the puzzle that we have is, okay, how is it possible that this operator has dimension exactly d minus 1? Okay, so what is it that, like, there has to be some mechanism, there has to be something that protects the dimension of this operator. Like, what's the magic going on here? And the answer that I'm going to explain now is that there is some symmetry in this Hamiltonian, which is a shift symmetry, and this symmetry is protecting this virial current. And it forces it to have dimension d minus 1, and therefore the virial current has the correct dimension, and therefore the system is only scale but not conformal invariant. Okay, so is the logic clear of like the, let's say, the argument in whole? Or if not, because now I'm going to explain like how this thing is protected, but maybe it's good if it's clear what I'm trying to achieve.
Yeah, it's very clear. Yeah.
It's clear? Okay, good. So let me explain this in some detail. So okay, now first let me explain what's the shift symmetry. So all these fields here, U, phi, etc., they all depend on space-time, right? Like you have like U as a function of x, where x is like some point in space-time. And now a shift symmetry is like a symmetry where you shift like some space-time dependent operator U, and then you shift it by some constant. Okay, so in particular, let's take this action. Let's say that we shift U by a constant. Remember, you can always integrate this thing by parts. And by doing integration by parts, you are always going to kill this constant, right? So you can just think of this as diu phi. And now if this term, you write it like this, then it's clear that you can always shift U by a constant. And that's the symmetry that is going to protect our virial current. Let me show you the argument because it's also very simple. So we have this symmetry. Now we do this procedure called Nether's procedure, which is just like some trick that tells you what's the conserved current for a certain symmetry. So in particular here you do this, you run this argument, and you see that the Nether's current for this symmetry is the field phi itself. Now, since we are in some kind of quantum theory, what you do is that you can construct from the current, you can construct a charge. And to construct a charge, what you do is that you integrate over some codimension 1 surface. Okay, and then here you just do like dimensional analysis. And what you see is that the dimension of the charge is just the dimension of phi. But then here you are integrating over d minus 1 dimension. So then you have delta q is delta phi minus d plus 1. Okay, like it's very simple algebra. And now you have that this charge here, it generates like the symmetry. So in particular, when you think of these things as some operators, then when Q acts on the operator U, it's going to give you the identity. Okay, because like this transformation just sends U to U plus a constant. So infinitesimally, like Q times U, it's going to give you 1. And then this symmetry doesn't act on phi, and therefore Q times phi, it commutes, it gives 0. And now remember that I was saying that our virial current, it's essentially U times phi. So now you do commutator with this object, then Q times U, Q commutator U gives 1, Q commutator phi gives 0. So then what you get again is phi. Okay, so now here you just do dimensional analysis. Q had dimension delta phi minus d plus 1. This is delta v, and this is delta phi. So by doing this dimensional analysis, you see that delta phi cancels out. And you see that delta v has to have dimension exactly d minus 1. Okay, so this is like some kind of abstract argument that immediately tells you that this virial current has to have like the right dimension to be a good virial current. Okay, and the way we saw this the fact that it's protected is thanks to this shift symmetry. Like we were acting here with this shift charge. Okay. And that resolves, like this very simple argument resolves the puzzle for our dipolar model. Like how is it that our dipolar model is only scale invariant? But here you might wonder, okay, is this argument even more general? Like, can you apply it to other theories? So let me consider like some abstract, like here I'm forgetting completely about dipolar interactions, and I'm considering some theory that has some operator O, and this operator has a symmetry under shift. So you can send O to O plus a constant, and that's the symmetry of your theory. Now what's going to happen? Well, there's going to be some shift current, and then this shift current is going to generate some charge. And then this charge, when it acts on O, is just going to give you the identity. Okay, so that's the definition of having a shift symmetry. And now by doing just dimensional analysis again, you're going to see that the current that implements like this shift symmetry, it has dimension d minus 1 minus delta O. Okay, and now you run the same argument as before. So we have some current, we can compute its 2-point function, and its 2-point function is actually fixed, like it has some relative coefficient, which is fixed because this is conserved, right? So you have that delta mu j mu, it has to be equal to 0. So this is going to fix this relative coefficient. But also like the dimension of j was fixed from this type of dimensional analysis here. So you can actually see that this constant here will not be the number that is required for conformal symmetry. So in general, like this very simple argument is telling us that theories with the shift symmetry will not be conformal, like in general. Like there's some exceptions that I'm not going to go into, but like theories with, like just to give the conclusion, theories that are interacting and have a shift symmetry are only scale, but not conformal invariant. Okay, like we have some argument here. I just gave you like the outline of the argument, but we have like some more precise versions. Let's see how I'm doing on time. Okay, and now I'm almost done. So here I have like another argument for how the shift current is, the virial current is protected, and it goes like very similar. So you can see that we looked at many examples, and we always see that the virial current is essentially the shift current multiplying the operator O with this, which is charged under it. And then you do like a simple like commutator here. You see that certain term, like the O cancels out. Then you just look at the dimensions of things, and you end up seeing that the virial current is always protected. Okay, so any theory that has a shift symmetry, it actually has some operator that could potentially be the virial current. And we did the calculation in some examples that we know of, and it always works out like this. So in fact, as I was saying, we went through the literature, and we saw that all examples that people came up with of theories that have scale but not conformal invariant, all examples fall under like our framework of like all of them actually have shift symmetries. And sometimes it was not even appreciated that was the reason that they were scale invariant. And in fact, in some cases, they understood that they had the shift symmetry, like for instance here, but they thought it was conformal. And I think our arguments show that they are incorrect, that it's actually only scale invariant. So let me maybe conclude. So they asked me to finish early, so I think I'm doing all right. So let me summarize what I've been explaining today. So I wanted to argue that when you look at real ferromagnets, you actually need to consider dipolar effects. And then like this raised like some puzzles, no? Like why is it that experiments actually agree with Heisenberg? And the answer that I gave is that dipolar effects are sometimes small, and they are only visible after doing some crossover from Heisenberg to dipolar. So actually many experiments, they are done in the Heisenberg regime. Like many experiments, they don't have enough resolution to see these dipolar effects. But we are hoping that like nowadays, like experimental resolution is improving and these dipolar effects will be observed. Now, the second thing I was asking is, okay, so I'm claiming that there's dipolar effects. So where do you see them? And I try to argue that where you see them is in this suppression of these longitudinal fluctuations. So essentially what the dipolar effect is doing to you is it's suppressing one of the three fluctuations you have, like in particular the longitudinal one. And that's gonna mean that like your 2-point function, like your 2-point function is gonna be like 5i, and it's gonna be like, I don't know, delta ij minus qi qj over q squared. Right, that's like there's going to be some overall factor like this, and this is something that can be observed in experiments. So that's the way to see dipolar effects. Now the other question was, okay, so this dipolar model, how is it possible that it's not conformal? And the answer that I just gave is that it enjoys some shift symmetry, and this shift symmetry protects the virial current. And finally, like I was wondering, okay, are there other examples that are somewhat similar to this? And in fact, yes. We looked at the literature, and all examples that we know of, they are of the same type. There's always some shift symmetry, and this shift symmetry is protecting the virial current, and therefore it's okay that there's only scale invariance but not conformal invariant. And that's everything I wanted to say. So thanks a lot, and I'm looking forward to hearing more questions.
Well, thank you so much, Aleix. Fantastic. That's very nice. And also thank you for the very clear talk. And I asked already some questions, but so please feel free. I mean, let's see if someone from the audience has questions. Please, don't hesitate.
So I have a very like naive question, maybe.
Yeah.
So in your example, like the shift symmetry that you have for like dipolar systems, it's related to actually like a Lagrange multiplier.
Yes, correct.
So in the other examples that you found in the literature, is this shift symmetry related to like something more directly physical, or is it often like something like a Lagrange multiplier? Or
in fact, it can come from several different sources. So one of the examples we look at is some kind of fluctuating membranes. And then in that case, like you have, let's say, we have 3 space dimensions, and then we have some 2-dimensional membrane that is fluctuating. And in this case, you can think of it as like the system actually has like a whole lot of symmetries, like rotational symmetries and so on. But then when you put a membrane there, what you get is that this, like the configuration of this membrane is spontaneously breaking part of these symmetries. Like there's some vacuum configuration of this membrane, like let's say it's oriented like this or like that or like that. That's gonna break, for instance, rotation symmetry. It's gonna break like some translational symmetry and so on. And then it's well known that when you have a spontaneous symmetry breaking, that leads to something that are called like Goldstone bosons or something similar. And then like these Goldstone bosons, they have some like they are coupled through derivatives like here, and then they always have some shift symmetries. So in particular, some of the example like one of the nice examples we looked at, it has the shift symmetry because of spontaneous symmetry breaking. So that's another like general mechanism how you can obtain shift symmetries. But yeah, more generally, I don't have like a more like each example is a bit different. So yeah.
But Aleix, now a very stupid comment.
Yes, please.
Like a free field, a free scalar field.
Yes.
Is a,
That's
it has a shift symmetry, but it's conformal.
That is correct. So then what's the what goes wrong in my argument? In fact, remember that was my very general argument. Okay, I was saying you have some free field, and then this free field can be shifted by a constant, and then you do this whole thing, and you compute what's delta J, and then you do this calculation, and you say, oh well, this doesn't look like the 2-point function of a primary operator. In fact, for the free field, you need to check an extra thing, which is that this J might be a descendant. So for a free field, what you have is that J free, let's say, mu is d mu phi. And then this thing is conserved because this field is free, right? Like this squared phi.
Yes.
Yeah,
yes.
Sorry for the bad handwriting.
No, it's perfect.
So then like this shift current for the free field is actually a descendant. And it turns out that for a descendant, this coefficient doesn't need to be 2. Like this coefficient I was calling alpha equals to 2. It actually has to be some other number. And it happens that everything works out nicely such that the number you obtain for a descendant, it precisely matches the number you get like from conservation. So in fact, for like a free scalar, it also works out. But we actually have an argument that more generally, even if this current is a descendant, in general, unless the theory is free, like that's why here I'm calling it interacting.
Yes, but then this conclusion does not explain why 3D Maxwell theory is like it's so in free Maxwell theory in 3D.
Yes,
there's a shift symmetry. It's not conformal. But so you're saying that for certain free theories, shift symmetry is enough to imply that the theory is not conformal, but
exactly.
Not
if it's interacting, we believe that again, like it's one of these genericity arguments. So
no, I understand, but I'm saying what instead, like, can you actually use the same argument to prove that does your argument work to prove that Maxwell field in 3D is it is not conformal, it is scaled without conformal?
So for instance, actually this Maxwell field is a nice example, because if you like if we were discussing this like recently with someone, like maybe I'm gonna say something wrong, but like the idea is that you can actually do like you can do a duality transformation, and then this Maxwell theory is going to be equivalent to some scalar, right?
Yeah.
Actually a free scalar, and this free scalar actually has a shift symmetry. And in fact, like here, there's like a subtle distinction that was a very good point that was said by Julio and Julio Parra. And what he was saying is that it depends on like this is going to be a compact scalar.
Yes.
But then like there's some RG flow where like in VIR, like this circle goes to infinity, and then you have to distinguish when like the shift symmetry emerges like in the IR when like this circle is infinite. So you actually have to be very careful, like which Maxwell theory you say that is a scale invariant. Like is it like there's some RG flow in this Maxwell theory, and you have to be careful. Like if you look at the UV free Maxwell theory or the IR free Maxwell theory.
Yeah, I agree, because they yeah, I understand. I actually meant
it's a subtle example indeed.
Yes, yeah, okay.
Yeah.
I understand, but I mean, no, very, very nice. So, are there any other questions?
Perhaps I have one. So, if I understand, so basically, you gave some argument why shift symmetry plus perhaps some other hypothesis might be a sufficient condition for having scale without conformal invariance. Then at the end, you said you also, all the examples you know actually have shift symmetry. So do you have perhaps some argument also why it might be necessary?
Yeah, no, we don't really have that. We don't know if it's true or not. The thing is that actually, like, what most people think is that many people think, oh yeah, all fixed points are actually like CFTs, and in fact, like over the last, let's say, 10 years, people came up with a bunch of counterexamples to this statement. So they came up with some counterexamples that are only scale invariant. And then like all these counterexamples we can explain, but it's true that it might be that now, like next year, someone comes up with another counterexample to this like general law. And maybe this other counterexample doesn't rely on shift symmetry. I think it's still going to rely on some funny symmetry or some extra property of this theory. Like I would imagine it's going to be like some kind of special theory, but I cannot prove it. So you are right. Like here, there's some work to be done for sure. But thanks, it's a good question.
Thank you. Actually, another small thing. So also, essentially your argument is, if you have shift symmetry, then this protects vector d-1. So this is a candidate for the virial current. But then
correct.
It might still be that you have the vector dimension d-1, but it's not the virial current.
So that's correct.
Or do you have an argument to say if there is such a vector, then it?
Yeah, the argument actually goes in two parts. So like the first part of the argument is, okay, you have the shift symmetry, and then you can compute the dimension of the shift current. And you actually see that the dimension of the shift current, it's not d-1, it's d-1 minus delta O. But conformal invariance forces conserved operators to have dimension d-1. So this argument already shows you that shift symmetry implies only scale invariance. But like so the first step is to show that this thing is only scale invariant, and now you have the puzzle. Okay, it's only scale invariant, but then what about the virial current? Like how come it's conserved? Sorry, it's protected. And then like for this puzzle, we have like this general argument that explains why it's protected. But I think our argument is nice in the sense that it's not only that you have a candidate virial current. I agree, like this operator might not appear in the trace of the stress tensor. It's not only that we have this candidate. In fact, like this argument shows you that except for this case where the field is free and then like this is actually a descendant and so on, like except for these very funny cases, like this argument already shows you that there's not going to be scaling, there's not going to be conformal invariance.
Okay, thanks.
Yeah.
Okay, great. So any other question from the audience? Okay, so I want to thank you, Aleix, once again for this very nice talk.
Thanks for the invitation. It was really nice to be here.